name's Ryan Chard. I'm a postdoc at Argonne National Laboratory, and I'm part of the Globus Labs group. So my bosses, Ian, Foster, and co, they run Globus, and they've got a research department called Globus Labs, and I'm part of that. So I'm here to talk to you guys about FuncX, a function serving system for HPC. As we've already alluded to, the name's a bit of a nightmare. Apparently it gets worse with my accent as well, so it's never a good thing. Yeah. So I don't know, if anybody has any better suggestions, feel free to hit me up. So first things first, a little outline. I can't actually see, there we go. So we've got some motivation for why we're trying to do this work. Essentially, we want to be able to support function-based workloads on HPC systems. I've got a little example of the implementation that we're going through called FuncX, and some preliminary applications that we're applying this to. So while I'm here to tell you guys what I've been doing and what we're working on, half of the reason I actually came out here, well, besides it being the warmest I've been in quite some time, is to try to pick your brains. So I'm not a Singularity expert. Many of you people are. So I'm definitely here to try to get some information on how I could be improving this. And just side note, this is half of our team. We're a pretty big team now. I'm on the corner, the tanned one. I don't know how that happened. Tyler is the guy next to me. He's our PhD student. He's been working on the implementation of this. And we've got our fearless leader up the top there, Ian. So, cool. Okay, so for some motivation. Essentially, we're of the opinion that HPC systems aren't really perfectly matched to many of the workloads that are coming out of scientific domains now. So we're arguing that many of these big scientific instruments, the APS, that's a photon source at Argonne, some scanning electron microscopes that we're working with a lot at Argonne at the moment as well, and even just general interactive computing don't really map well into the HPC world of batch computing, essentially. I've got a picture here of sporadic scientific research. This is some work I used to do with a group of genomics research portals. And essentially it shows the number of jobs each day over a 150-odd day period. And you can see that it's extremely sporadic. It's not the example workload or the best workload that you could apply to an HPC system. So this is what we're trying to accommodate. These workloads, or these sources of data, are not running 24/7. SEM machines only run when somebody's sitting there clicking the button. The APS goes down every 2 weeks. You only get beam time once every month or so for a couple of days. And that's when data is generated, and we need to be able to support analyzing that data sort of on demand on big HPC systems. So there's a number of barriers to HPC systems. As many of you, I'm sure, are aware, this is sort of a field you guys work in. So obviously there's a number of issues or constraints for actually using these systems on demand, especially for novice users. So, well, people that aren't especially tuned to these big machines. So I've got a small list of them here. There's a variety of different architectures, accelerators. Being able to use these different things can be challenging. There's a big learning curve. One of my master's students 2 weeks ago was complaining that the GCC package on a Singaporean supercomputer was so old he couldn't run his genomics workloads. And then I introduced him to package management. So he didn't realize that there was things out there like module load. So he was stuck with the old systems, and it just wasn't working. Different interfaces, of course, at Argonne we run Cobalt, good. Difficult to acquire resources in a timely manner. Quite often you'll send off your job and you'll get some sort of notification back an hour later that you've actually started. And you can't really reserve these resources without actually having work. ALCF, our leadership computing facility, they don't really want you acquiring 100 nodes, 50 nodes, and just sitting there waiting for your jobs at the beamline to actually start generating data. And then another point I've got here is that small tasks aren't really an HPC problem. So these short duration, on-demand analyses, they're not really designed for HPC. Mike Papka, the director of the ALCF, told us such. However, as soon as you've got thousands of them, these are problems that need to be addressed, essentially, or supported at least. Okay, so where are we going? Serverless computing. I assume everyone's heard of serverless computing. It's all the rage. It's taken over enterprise IT as a way to minimize costs or reduce costs and make your stuff infinitely scalable. It's brilliant. Function as a service is a big part of this. So pretty much every cloud manufacturer has some sort of function as a service platform, whether it's Lambda or Google Cloud Functions or what have you. And essentially, we want to take these things and be able to apply them to our HPC. So give users a nice new interface that lets them interact with their big computers where we will manage the actual infrastructure in terms of scaling it up and down. Yeah, that'll do. So FAS for science, function as a service. The goals here are essentially threefold. So one, we want to remove barriers and simplify usage. So that's obviously one of our big motivators. We really want to abstract all of the computing in general. If we can just have users click a button or hit a REST service and their jobs are run, that would be ideal. Containers make tasks portable. Somebody else's talk told me that this isn't correct, so I'm going to need to talk to somebody about that a little bit more. And then, yeah, we really want to be able to support a new generation of applications. So there's a lot of these real-time workloads out there. We've got a Jupyter Hub environment at Argonne. We want to be able to spread these jobs on demand onto ALCF resources. And in addition to this, the work I do with the beamlines, we'd really like to be able to do guiding of experiments, and much of that is dictated by model in the loop. So using machine learning in your scientific process to sort of guide where your experiments are going on demand. Yeah, and all of this, function as a service, really gives us a lot of opportunities to do some more optimization for these different tasks. So being able to exploit backfill for these tasks would be really nice. Okay, so whereabouts are we going? FuncX, good. The goal of this is essentially to enable these secure execution of functions on HPC infrastructures. We really want to get rid of that infrastructure barrier to users. And we want to be able to do all of this securely with access management and logging and allocation tracking and all of that sort of good stuff. And then finally, as a result of this, we really want to be able to establish a library of these functions that really promote reusability and reuse. So that would be a plus. So just to quickly make sure we're all on the same page, we've got essentially two components here. We'll get into that. There's functions, which in my world are stateless, short running or short duration tasks, whether they're actually a function or a small script, that's neither here nor there. The word stateless really threw some of my high energy physics colleagues through the loop, but we'll get around that. Essentially what I'm trying to say is at the conclusion of this task, if you don't take your data away, that container or however that task was run, its storage is ephemeral and it's going to get deleted, unless you deliberately stage it somewhere else. Invoked on demand, so we really want to have a nice REST API to actually be able to do this. And yeah, accept some sort of blob of information and act on that. You can work that out. And runtime. So a runtime is essentially a container or a set of dependencies. So maybe it's pip modules that you would need to install into your container or into your runtime to actually be able to run your function. It's a method of isolation. So hopefully something running inside this container doesn't interfere with other functions running inside their own containers. And yeah, well, okay, serving multiple functions. That's one of our goals for optimization later on. Okay, so I drew this lovely picture, and we'll quickly go over some of these design aspects of how we intend to build this thing, then I'll talk about the actual prototype that we have done. So this is very high level. Essentially, we're going to have something sitting in the cloud that users interact with. You would have a REST API on it. You would hit that thing, tell it to run this function, create a function, do whatever you want. We're going to have this hierarchical execution model, which interacts with the low-level resources where jobs actually run. We're going to do that with pilot jobs. I'm sure you're all familiar with this. And then we're going to use containers as an isolation mechanism actually to perform these tasks. Okay, so just jumping into this a little bit more. So at our cloud web service, we're going to have a client, some sort of thing that's interacting with all of this execution hierarchy. So this client you're going to be able to communicate with. This will happen behind the scenes of a REST interface where it would be able to, essentially it's got two jobs. One is to deploy interchanges. So that is deploying the thing that's actually going to do the work on some remote resource, whether that's ALCFs, Cooley, or Theta, or whatever. And the second one is to actually submit jobs to it. So when you hit a REST request to start a function, it's going to communicate with this client, this FuncX executor, and actually pass that job off. Yeah, so deploying interchanges, I'm sure you guys are familiar with how annoying authentication is. It's the bane of my existence. So we need our way of deploying these interchanges to actually support crypto cards and all of that good stuff. We need to, what else have we got here? Submit a task and receive a future. So once we submit a task, we need to be able to monitor what's actually happening with it. And then we need to serialize the app inputs. So this is the final task of this, this client thing, serialize the inputs in the function and send them down to whatever's actually going to execute this job. The second part, the interchange. So we've moved from the cloud now. This is what the client thing started on the remote resource, whether this is your coolly login node. I love login nodes. We'll deploy this thing here so it's actually running on the resource. It connects back to our client to receive jobs. It interfaces with the remote resource. So this is how we actually acquire nodes and deploy managers on these resources. And it's got a whole bunch of watchdogging and batching and all of that good stuff built in that will let us monitor the managers that we deploy on the compute nodes and make sure they're all alive and doing what they should be doing. The managers, so this is the thing that's actually deployed on the compute node. So we've now gone from a login node to one of our actual resources, the compute workers. These things, once deployed, are essentially an abstraction of the resources on that compute node, so however many CPUs it's got, and some number of worker threads. So this thing starts a number of worker threads. They all sort of get allocated one portion of that compute node, and then basically are listening for tasks from this thing. What else do we say here? Maintain a cache of runtimes. Okay, somebody's probably going to ask how we're pushing all of these around. We use Globus, obviously. I am Globus. Rick, don't tell people I said that. So, yeah, so we'll push these things around. Just don't tell them about it, and they'll never look. It's fine. So yeah, we have to maintain some sort of cache of these runtimes so our workers actually have something to execute on them. We need to be able to push these down to our workers. We're assuming for our version 1 prototype that all of these share a shared file system. So we've just got a nice directory sitting there holding all of those container images. And then finally, we've got our workers. So essentially, these are a thread that is running on that compute node. There'll be a pool of them. It's called a thread pool. And these things, yeah, they receive tasks from the managers, and then they use Singularity containers to actually execute the task and go for gold from there. And then obviously send everything back up the stack to get our results back to users. Okay, so moving on to our prototype. I need to point out that this is preliminary work. I don't know how long ago we started this, a month or so ago. The plan is to acquire funding to actually build a real version of this. And Tyler Skluzarczyk has been helping me build this thing out. So we've pretty much taken the previous design and implemented all of that. Some quick assumptions around this. One, we're assuming it's single tenant, so we're not worrying at the moment about building a multi-tenant solution. Two, we've built all of this on Parcel. Has anyone here ever heard of Parcel? You guys are in for a treat tomorrow when Rick talks about it. Parcel is a parallel scripting library built out of the University of Chicago. It's really powerful for interacting with remote resources and acquiring nodes for sort of any sort of arbitrary resource you've got there. Obviously, we're building Globus Auth and Transfer, so Auth does all of our identity management. And then we use Singularity runtimes as a means to do this packaging of dependencies and our initial steps towards isolation. Okay, development status ongoing. So please don't rip me apart if you see something that you don't believe works, because it probably doesn't. Okay, FuncX and Parcel. So Parcel is really powerful, this thing. It's got these different executors in it. So we've actually shown with the extreme scale executor, XX. You might see the trend now of where FuncX came from. XX can scale to, I think, 5,000 nodes on Theta, or 4,800, however many it's got. And it can scale to over 50,000 tasks, which Rick will talk about tomorrow. We've got these other ones, high throughput, low latency, and now FuncX. Essentially, we've got different executors based on the different roles or tasks that you want to actually be doing. And then down in the corner is a brief overview of how you actually define a resource such that Parcel can connect to it and submit jobs through whatever queue you specify. This is using a Slurm provider and whatever SSH channel if it's local or some sort of interactive thing. So yeah, we use Parsl to build our thing. Essentially, we've implemented a new executor that does the thread pool maintenance and the use of Singularity containers to execute tasks. Globus, obviously, Globus everywhere, taking over the world. we use it to move our runtimes around, move big data sets around, and obviously our auth and login. So you have to log into our system with one of the identity providers, whether it's your university credentials, what have you. And this allows us to track all usage through our system. It's really nice for all of that. Yeah. And finally, our tasks. So actually executing these things. We've done all of this with Singularity, otherwise I probably wouldn't be here. Essentially, we've got these interchanges that acquire the compute resources, and then they start a bunch of workers on these compute nodes, and then our workers receive a task off this queue, and they go through the following steps. So this is something that I really need to flesh out. Currently, it does this. I'm sure you guys will see gaping errors with it, so please talk to me if you want to help me fix this. The first thing the idle worker does once it gets a task is it creates a new namespace directory. It just makes a directory with the time and some user-specified thing about what the function is. Deserializes the function into that directory so we can actually execute it. Pulls up one of our Singularity containers and actually runs the task. So it runs that function, and then it passes all of that stuff back up the chain. So one thing I've been trying to do is do the sandboxing a bit better, because ideally we don't want these functions interacting with each other. I started off trying to use LXCs. That didn't work. I had issues with connecting to the daemon process. Maybe you guys know why. My next step was to use user IDs, essentially, create a new user for the user invoking the task, set permissions on that directory, then restrict that directory to that function. But I don't know. We're going to have to fix this somehow. Currently, it's not very secure, so story of my life. Dynamically build runtimes. So that's sort of the next thing as well. Currently, we're assuming all of our functions share the same dependencies, so we can just have one container serve every function in our system. Ideally, we want to remote build these, perhaps. I don't know. I just learned about that today. So yeah, building these containers on demand based on the requirements or dependencies specified when you publish this function. That's sort of where we want to go. Okay, so some preliminary work. I have no idea how long I'm taking here, but this is good. There we go. Plenty of time. Oh, heaps of time. Okay, good. Perfect. All right, so my accent does help with speed. But yes, okay, so to talk about this a little bit, we've got three really driving use cases here. We've actually got a fourth one around serial crystallography, which is a really cool use case for this stuff because they suddenly get 25,000 images of different protein crystals out of these little chips. And then they need to very quickly threshold these to see if there's any crystal information in there using this dials tool. I don't talk about this here, but it's a really good driving use case for why we want to spray off a bunch of little functions and do some thresholding and sort of map reduce those results back in. Okay, so our preliminary work really focuses on DLHub, which is the data and learning hub for science that I've been working on at Argonne National Lab. Globus Automate, which is our automation system that I've been working on at Argonne and Globus. And Extract, which is Tyler's PhD project, which I help him out on. This is a metadata extraction system that we've been working through. Okay, so first things first, DLHub. So DLHub is really a model repository and serving system. So the idea is to take or to build a system where people can take their machine learning models and actually publish them for people to later find, use, build on. Yeah, really, we had this problem in material science. This is where this work came from with Ben Blazek as a PI. So in material science, every man and their dog is using machine learning to find some new property. Then there's 1,000,001 papers being published on using machine learning to do something, and you can never find those machine learning models afterwards. So we built DLHub as a way to sort of catalog or archive and have a big store for these different machine learning models, and then we put serving capabilities on top of it so you can invoke these models sort of on demand. And we're trying to answer the following questions of where is the model and the trained weights that you're publishing about? How do I actually use the model to use it on my own data? Should I be using the model? So attaching some metadata about what you should be using it for, and working through how we actually go about retraining this model and so on and so forth. So DLHub and FuncX, this actually is a pretty nice partnership because the way we work in DLHub is currently we containerize every machine learning model and then put it on a Kubernetes cluster. So ideally, we would containerize these things in Singularity and just throw them on a Kubernetes cluster and use FuncX as our invocation pipeline. This gives us a lot of benefits. FuncX is very low latency because we're built on top of Parcel's low latency executor, which is all ZMQ pipes the whole way down. And it already interfaces with both the HPC systems and Kubernetes, so we can very easily move DLHub over to FuncX, which is going to save a lot of hassle. The other thing here is it's going to enable training on HPC resources. So one thing DLHub doesn't do at the moment is training. So you can do on-demand inference of these things, but you can't go and start a long-running task on a big machine, simply because we don't have interfacing to big machines. So putting DLHub in here really gives us an opportunity to exploit these ALCF resources for on-demand training, which is going to be nice. So yeah, really where we're going with this is FuncX fills both of these problems of serving on demand and doing remote training. So that's why we're very happy to be moving to FuncX in DLHub. And I think I'm going to push the button tomorrow to actually switch it over, which will be a plus. Automate, so this one's near and dear to my heart. I worked on this for about the last year to build out a automation system, which has now received NSF funding and is being converted into a Globus product. I'm pretty sure I'm not meant to say this, but that's fine. It should be online. I don't know, I should give a deadline. Venvo, watch this. That's all right. But yeah, so this one's going to be online in the next year or so, I think, for people to actually start using. There's already prototypes of it around. If you are interested in using our Globus Automate product, come to me. I'm currently rolling out all of our use cases. Essentially, it's a distributed research data management system where you define a data management pipeline, which may step between different services. So obviously, I work with Globus, so services you can step to are things like transfer, where you would move data between two Globus endpoints, catalog, where we can ingest data into a search index. We've got auth, so you can set access controls on your data, and sharing and so forth and whatever. Where FuncX comes in is now you can use this pipeline to step to a compute resource and run some analysis on your data as well. So we've been using this to actually facilitate a neuroanatomy automation. So I work with a bunch of neuroscientists at the APS. They've got some fascinating problems where they're trying to image entire mouse brains, which sounds small, but that's a heck of a lot of data. So yeah, this pipeline is essentially they take an image of a mouse brain or octopus brain or fish brain. They do a lot of brains. You take an image of that at the APS, and then that gets stored immediately on a co-located machine called TXM1. And then that moves. This is actually funny because this is the slowest part in this entire workflow. It moves a foot to TXM2 and takes about 3 minutes or so to actually do that. Once it's at TXM2, that's where I'm allowed to take over. So I've got some, we've put a Globus endpoint on there. And we start a flow in response to that data being generated, which moves that data over to ALCF, does some compute to extract some preview images and some center information, so working out whether or not the beamline was actually online. And then asks the user for some validation, does a full reconstruction based on the user input if they agree that that image was correct. And then we do the publication pipeline and visualization with a NeuroGlancer system that we've set up at UC. Yeah, so FuncX really gives us a nice way to accommodate this flow. Before FuncX existed, we had Ryan deploy, I'm Ryan, sorry, I like to do that. We had me deploy a very insecure little script that would call out to a web service and see if it has any jobs. And if it does, it would just run. So there was no security in there at all. I was bypassing everything. Everything was running on my behalf. ALCF never found out, so provided we never tell them, we're good. But now we've got FuncX, so we can step to this service. We can step to this reliable web service sitting on AWS, which will start a connection down to our machines and then run your tasks on demand. Cool. So yeah, that's sort of where this flow goes. We do it for both of them, the preview generation and the full reconstructions, and then we carry on from there. Okay, our last one. So we've got extract. I forgot to take the E out. Ian told us last week we need to rename it, so it was Googleable. So yeah, we've got extract, which is a metadata extraction system. Essentially, the problem Tyler faces, so this is Tyler's PhD work, is that scientific repositories are an absolute mess. He found one called CDAC, which is a climate repository. It's got 500,000 files in it. It's like 500,001 files in it. And I think the third or fourth most common file extension is having no extension. So it's ridiculous how bad this is. So they've gone and built a system that uses containers to process these data and try to pull out a bunch of metadata and then push that into a catalog. So this one here is really cool. If you give it a map, one of our students built a map extractor, uses some sort of ML technique to trace out the islands in it, what I call South America and Ireland, and then it does some sort of lookup to find out what tags to actually put on this, and then it goes through and tags Chile, Argentina, and so on and so forth, which is pretty impressive. And then we can take that metadata and throw it into a big repository. So why FuncX is important here and why we're using this as a driving factor is because currently extract has to pull all of the data to itself. We run extract hub on PetrolCube, our Kubernetes cluster, where it transfers data to itself, runs the containers, and then pushes the metadata somewhere. Ideally, we would be pushing these functions to the data, so actually taking our containerized execution, extraction little scripts and pushing them down to very large data sets and running them on demand. And one of our big sort of goals here is to be able to do this with backfill, so we can take up the backfill cluster and start slowly extracting all of the metadata about your files on some scientific store. Yeah, I think that's pretty much it. Cool. So if anybody has any comments about what I could be doing better in this, has any opinions on how I should be using Singularity to do this stuff, I'd love to talk to you guys. If anybody wants to get involved, I think this has potential to go somewhere. Could be fun. Feel free to come and chat. Go. Questions?
Great. Any questions for Ryan before he commits another career-limiting move? I think we're up to 3 or 4.
Yeah, fair enough.
It's all recorded. Don't worry about it. Anyone? I think the group is probably getting tired.
We're close to here.
Thank you. It's very interesting.
Cool.
Certainly have some things to chat with you about later, especially the Kubernetes angle. Question?
Well, actually, I guess feedback.
Whoa. Rick, I'm only going to move so fast at this point. Sorry.
It's all right, Ass.
Oh, jeez. Not everybody caught that.
Separated at birth. Actually, so feedback from the group. One of the things from working with Ryan and talking with him about this is that FuncX to me strikes me as a way to templatize containers, right? Is if you imagine that we can make zip files that are executables with standardized inputs where I don't necessarily have to know what is the application in the container as long as I can pass the parameters in a standardized way as a JSON file. And what I'd be interested in is anyone else has that use case where if we can think of something like FuncX where it is a workflow engine that can take on the role of things like we used to do with Graham and other stuff that was very complex, very, again, my favorite word for HPC, idiosyncratic, and make it more generally usable, would they be applicable? What if we standardized on a template for container formats where it was dash parameters, JSON file name, and it got passed in, and FuncX could use that, something else could use that, and now it's like, I know I can call this even if I'm not exactly sure what's in it.
Sounds like, oh, here we go. Definitely worth continuing that conversation. Uptown FuncX, is that what you're thinking? Yeah.
Yeah, I was sharing similar thought on my one of the slide where we say, I just picked Mellanox software as an example, but I think it has more generic use case where you say, I'm going to keep only my small application in the container, but I want these functions or libraries to be mapped to me where you define a standard component saying we want these functions to be available to process the data. And that Kubernetes has something called CRD, and which is sort of for the resource, but not for the libraries and packages. So one container can ask to have another container, for example, to provide all the libraries through a bind mount, and which is a read-only format. Get over it. If I'm running 100 containers, my container image is still small to be of that small application. But there is one container who is providing me these heavy lift libraries to be mapped in my middleware. As it's not exactly, I don't know how to pronounce it, FuncX, where you request a remote service. This is still a local service to be mapped to